There is something in the universe that we cannot see, cannot touch, cannot directly detect, yet without it, galaxies would fly apart, clusters would dissolve, and the cosmic web itself would unravel. It outweighs all the stars, planets, gas, and dust combined. It shaped the formation of galaxies in the early universe. It determines how fast stars orbit in spiral arms. It bends light from distant galaxies like an invisible lens. And yet, despite decades of searching, no one knows what it is. This is the mystery of dark matter. Zwicky's calculations revealed a problem. The galaxies were moving far too fast. Based on the visible matter stars and gas, the cluster did not have nearly enough mass to hold itself together. The galaxy should have flown apart billions of years ago. Zwicky concluded that there must be additional unseen mass providing extra gravity. He called it Dunkel Materiae, dark matter. At the time, his idea was largely ignored. The astronomical community was skeptical, and the tools for further investigation were limited. The mystery resurfaced decades later in a far more compelling way. In the 1970s, astronomer Vera Rubin began studying the rotation curves of spiral galaxies. A rotation curve shows how fast stars orbit at different distances from the galactic center. According to Newtonian physics, stars closer to the center, where most of the visible mass resides, should orbit faster than stars at the outskirts. Just as planets farther from the sun move more slowly, stars farther from the galactic center should slow down. But when Rubin and her collaborator, Kent Ford, measured the rotation of stars in galaxies like Andromeda, they found something astonishing. The outer stars were not slowing down. They were orbiting at nearly the same speed as stars much closer to the center. The rotation curve was flat. This meant that as you moved farther out, the amount of mass enclosed within the orbit kept increasing, far beyond what was visible. It was as if each galaxy were embedded within a massive, invisible halo of matter extending far beyond its luminous disk. This was no minor discrepancy. In many galaxies, the invisible mass appeared to outweigh the visible matter by a factor of 5 or more. The implications were profound. Dark matter was not just a feature of clusters. It surrounded individual galaxies as well. Over time, more evidence accumulated. Gravitational lensing provided another powerful clue. According to Einstein's general theory of relativity, massive objects bend space-time, causing light from background sources to curve as it passes nearby. This effect can magnify and distort distant galaxies when their light travels through a massive foreground cluster. By measuring the degree of lensing, astronomers can calculate the total mass of the cluster, including invisible components. Time and again, lensing measurements revealed far more mass than could be accounted for by visible matter alone. Perhaps the most dramatic example came from the Bullet Cluster. In this system, two galaxy clusters collided. The hot gas from each cluster slammed together and slowed down, glowing brightly in X-rays. But gravitational lensing maps showed that most of the mass had passed straight through the collision point without interacting. The visible gas lagged behind. The mass dominated by something invisible continued ahead. This separation provided some of the strongest evidence that dark matter is not just an artifact of modified gravity or observational error. It behaves like a separate substance interacting primarily through gravity. By the late 20th century, dark matter had become a cornerstone of cosmology. Measurements of the cosmic microwave background, the faint afterglow of the Big Bang revealed tiny fluctuations in the early universe. The patterns of these fluctuations depend sensitively on the universe's composition. Data from satellites like COBE, WMAP, and Planck showed that ordinary matter makes up only about 5% of the universe's total energy content. Dark matter accounts for about 27%. The rest, about 68%, is dark energy. Dark matter is more than 5 times as abundant as everything we can see. It forms the scaffolding of the cosmic web. In computer simulations of cosmic evolution, dark matter clumps together under gravity, forming halos and filaments. Ordinary matter falls into these dark matter wells, cooling and forming stars and galaxies. Without dark matter, the universe would look radically different. Galaxies would struggle to form. The early density fluctuations would not grow quickly enough to produce the structures we observe today. And yet, despite its dominance, dark matter has never been directly detected. We infer its existence from its gravitational effects, but we have never captured a dark matter particle in a detector. What could it be? It cannot be ordinary matter made of protons, neutrons, and electrons. If it were, it would interact with light-absorbing or emitting radiation. It would show up in astronomical observations. It does not. It must be composed of something else. One leading candidate is the WIMP, weakly interacting massive particle. WIMPs would interact with ordinary matter only through gravity and possibly the weak nuclear force. Billions of them could pass through your body every second without leaving a trace. Experiments deep underground, shielded from cosmic rays, are searching for rare collisions between WIMPs and atomic nuclei. So far, none have been confirmed. Another candidate is the axion, a hypothetical lightweight particle proposed to solve problems in quantum chromodynamics. Axions would be incredibly light and weakly interacting, yet could collectively account for dark matter. Other possibilities include sterile neutrinos, primordial black holes, or entirely new forms of matter beyond the standard model of particle physics. Each candidate comes with challenges. Particle accelerators like the Large Hadron Collider have searched for signs of dark matter production. No conclusive evidence has emerged. Underground detectors have grown increasingly sensitive. Still no signal. Astrophysical observations continue to confirm dark matter's gravitational presence, but they do not reveal its identity. Some scientists have proposed alternative explanations. Perhaps gravity behaves differently on galactic scales. Modified Newtonian dynamics, or MOND, attempts to adjust the laws of gravity to account for flat rotation curves without invoking dark matter. But while modified gravity can explain certain galactic observations, it struggles to account for clusters, gravitational lensing, and the cosmic microwave background simultaneously. Dark matter remains the simplest explanation consistent with all available data, yet it is profoundly unsatisfying. We have mapped its distribution across the universe. We have measured its abundance with precision, We have simulated its role in structure formation, but we do not know what it is. It is as if we have discovered that most of the ocean is made of an invisible substance, one that shapes currents and tides. Yet, we have never sampled it directly. Imagine looking up at the night sky and realizing that the stars you see are only a thin, luminous veneer stretched over a vast, invisible framework. The Milky Way, with its hundreds of billions of stars, is embedded within a dark matter halo extending far beyond its visible disk. Galaxies cluster along filaments of dark matter that span hundreds of millions of light years. Even the largest structures in the universe are defined by this unseen component. Dark matter may pass through itself and through ordinary matter without friction. It does not clump into stars or planets. It remains diffuse, forming halos and webs. Its presence is inferred from motion stars orbiting too fast, galaxies moving too quickly, light bending too strongly. In laboratories around the world, detectors sit in silence, waiting. Deep beneath mountains and inside old mines, ultra-pure crystals and liquid xenon chambers monitor for tiny flashes of light that might signal a dark matter interaction. Every so often, an anomaly appears. Hints of possible signals surface, but none have survived scrutiny. The mystery persists. Perhaps dark matter is not a particle at all. Perhaps it represents a new property of space-time. Perhaps it hints at dimensions beyond the familiar three of space and one of time. The implications are staggering. To solve dark matter would not merely add a new particle to the list of known entities. It would reshape fundamental physics. It would connect cosmology, the study of the largest scales, to particle physics, the study of the smallest. It would answer a question that has lingered for nearly a century. Why does gravity behave as if there is more mass than we can see? As telescopes become more powerful, they continue to refine our measurements of dark matter's distribution. Weak gravitational lensing surveys map its influence across vast cosmic volumes. Observations of galaxy collisions reveal how dark matter behaves in extreme conditions. Every line of evidence points to its existence, and yet the substance itself remains hidden. Among all the cosmic mysteries scientists cannot solve, dark matter stands at the forefront. It is not a distant anomaly or a rare phenomenon. It is the dominant form of matter in the universe. It surrounds us, it flows through us, and we have never seen it. Somewhere in the darkness between the stars, in the halos around galaxies, in the scaffolding of the cosmic web, dark matter exerts its quiet pull. The universe is heavier than it looks, and until we uncover the true nature of that hidden weight, one of the greatest mysteries of the cosmos remains unsolved. If dark matter is the invisible glue holding the universe together, then dark energy is the unseen force pulling it apart. It is stranger than dark matter, more elusive, and even more unsettling. While dark matter hides in halos around galaxies, dark energy appears to permeate all of space itself. It does not clump. It does not form structures. It does not pull things together. Instead, It pushes the universe outward faster and faster, and no one knows what it is. The discovery of dark energy in the late 20th century was one of the most shocking revelations in the history of science. For decades, cosmologists believed they understood the broad outline of cosmic expansion. Ever since Edwin Hubble discovered in 1929 that distant galaxies are receding from us, scientists have known that the universe is expanding. The Big Bang model suggested that everything began in a hot, dense state and has been spreading out ever since. But there was an open question. How fast is the universe expanding, and is that expansion slowing down? Gravity, after all, pulls matter together. The combined gravitational attraction of all the matter in the universe should gradually slow the expansion over time. Depending on how much matter there is, the expansion might slow to a crawl, halt entirely, or even reverse in a future big crunch. By the 1990s, astronomers had developed powerful new tools to measure cosmic expansion with unprecedented precision. Two independent research teams, the Supernova Cosmology Project and the High Z Supernova Search Team, set out to answer the question directly. They focused on a specific type of stellar explosion, type Ia supernovae. Type Ia supernovae occur when a white dwarf star accumulates matter from a companion until it reaches a critical mass and undergoes runaway thermonuclear fusion. Because this process occurs under similar conditions each time, these supernovae have nearly uniform intrinsic brightness that makes them excellent standard candles. By comparing how bright they appear to how bright they should be, astronomers can calculate their distance. The teams observed dozens of distant type Ia supernovae, measuring how far away they were and how fast their host galaxies were receding. They expected to find that distant supernovae were slightly brighter than predicted, indicating that the expansion of the universe had been slowing down over time. Instead, they found the opposite. The distant supernovae were dimmer than expected. They were farther away than they should have been if gravity were slowing expansion. The conclusion was staggering. The expansion of the universe is accelerating. Some unknown force is pushing galaxies apart faster and faster as time goes on. This force came to be known as dark energy. The name reflects our ignorance. We do not know what it is. We only know its effect. The implications are profound. Dark energy now appears to make up about 68% of the total energy content of the universe. Combined with dark matter, ordinary matter accounts for less than 5% of the cosmic budget. Everything we see, stars, planets, galaxies, is a minor ingredient in a universe dominated by unknown components. But how does dark energy work? One possibility is that it is a property of empty space itself. In Einstein's general theory of relativity, gravity is not a force in the traditional sense, but the curvature of space-time caused by mass and energy. Einstein originally introduced a term called the cosmological constant, a kind of repulsive energy inherent to space to keep the universe static, as he believed it must be. After Hubble discovered cosmic expansion, Einstein reportedly called the cosmological constant his greatest blunder. Yet decades later, The cosmological constant returned in a new context. If empty space contains a small but non-zero energy density, it would exert a repulsive gravitational effect, driving accelerated expansion. In this interpretation, dark energy is the cosmological constant. But this leads to a puzzle of extraordinary proportions. Quantum field theory predicts that empty space is not truly empty. It is filled with fluctuating energy fields. Even in a vacuum, virtual particles constantly appear and disappear. The energy associated with these fluctuations, vacuum energy, should contribute to the cosmological constant. However, when physicists calculate the expected vacuum energy density from quantum mechanics, they obtain a value that is 10^120 times larger than the observed value of dark energy. This discrepancy is the largest known mismatch between theory and observation in all of physics. It is not a small error. It is off by a factor of 100 billion, trillion, 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 trillion. Somehow, the vacuum energy predicted by quantum mechanics must almost perfectly cancel out, leaving only a tiny residual effect. Why? No one knows. This is sometimes called the cosmological constant problem. Another possibility is that dark energy is not constant at all. Perhaps it evolves over time. Some theories propose a dynamic field called quintessence that permeates space and changes its strength as the universe expands. If dark energy varies, it might offer clues to new physics beyond the standard model. Observationally, measuring the properties of dark energy is extraordinarily difficult. It does not emit light. It does not clump into galaxies. It only reveals itself through its influence on cosmic expansion. Astronomers measured dark energy by mapping the large-scale structure of the universe, how galaxies cluster, and how that clustering evolves over time. They also study baryon acoustic oscillations, subtle ripples in the distribution of galaxies left over from sound waves in the early universe. These measurements help determine how the expansion rate changes with distance and time. So far, the simplest explanation, a cosmological constant, fits the data reasonably well, but small discrepancies are emerging. One of the most intriguing is known as the Hubble tension. Different methods of measuring the expansion rate of the universe yield slightly different results. Measurements based on the cosmic microwave background suggests a slower expansion rate. Measurements based on nearby supernovae and Cepheid variable stars suggest a faster rate. The difference is small but statistically significant. It could point to unknown systematic errors, or it could hint at new physics, perhaps involving dark energy. If dark energy changes over time, it could affect the expansion history in subtle ways. The fate of the universe depends critically on the nature of dark energy. If it remains constant, expansion will continue accelerating indefinitely. Galaxies not gravitationally bound to us will eventually disappear beyond the cosmic horizon. The universe will grow colder and emptier over trillions of years. This scenario is sometimes called the Big Freeze or heat death. Stars will burn out, galaxies will fade, black holes will slowly evaporate through Hawking radiation. If dark energy increases in strength over time, a scenario known as phantom energy, the consequences could be more dramatic. In a hypothetical Big Rip, the expansion rate would grow so extreme that it would eventually overcome all forms of binding energy. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems, then planets. Eventually, even atoms could be ripped apart as space-time itself stretches to infinity. Current data do not favor such an extreme outcome, but the possibility cannot yet be ruled out entirely. Alternatively, dark energy could decay or change sign in the distant future, causing expansion to slow and perhaps reverse in a new big crunch. At present, observations suggest a constant, persistent acceleration. But the true nature of dark energy remains hidden. One of the strangest aspects of dark energy is that it appears uniform. Dark matter clumps into halos and filaments. Dark energy does not. It seems to have the same density everywhere, even in the emptiest regions of space. In fact, as the universe expands and matter becomes more diluted, the relative influence of dark energy grows stronger. In the early universe, matter dominated. Gravity shaped the formation of galaxies and clusters. Today, dark energy dominates. In the far future, it will overshadow all other components. This cosmic coincidence raises another mystery. Why is dark energy becoming dominant precisely now, in the epoch when observers like us exist? If it were much stronger, galaxies might never have formed. If it were much weaker, the universe might have collapsed before life emerged. Some physicists invoke the anthropic principle, the idea that we observe this balance because only universes with such properties can host observers. Others search for deeper explanations. The discovery of dark energy has reshaped cosmology. Before 1998, the central question was whether the universe would expand forever or collapse. Now the question is what dark energy is and how it behaves. In laboratories, physicists search for clues. In particle accelerators, they probe the quantum vacuum. In astronomical surveys, they map billions of galaxies. Every new measurement refines our understanding of cosmic expansion. Yet dark energy remains a placeholder, a name for something we do not understand. Imagine explaining to someone that nearly 70% of the universe consists of a substance that cannot be seen, cannot be detected directly, and whose nature is unknown. It would sound like fiction, yet it is the best description we have. The accelerating universe was not predicted. It was discovered by accident through careful measurement and unexpected results. This is the power of science, to follow the data even when it leads somewhere astonishing. Dark energy challenges our deepest intuitions about space and time. It suggests that empty space is not inert but dynamic, that the fabric of the cosmos carries energy, that the destiny of everything, from galaxies to atoms, depends on a property of vacuum itself. Among the cosmic mysteries scientists cannot solve, dark energy stands as one of the most profound. It shapes the future of the universe. It dominates the cosmic energy budget, and yet we do not know what it is. Perhaps future discoveries in quantum gravity or string theory will provide answers. Perhaps new observations will reveal subtle variations in its strength, or perhaps dark energy will remain. One of the enduring enigmas of the cosmos, a reminder that even with all our telescopes and equations, the universe still holds secrets at its very core. For now, we live in an accelerating universe. Galaxies drift apart at ever-increasing speeds. The cosmic web stretches thinner, and the force driving it all remains hidden, silent, pervasive, and unsolved. Every story has a beginning. Every explosion has a spark. Every expansion has a starting point. When it comes to the universe, that beginning is called the Big Bang. It is the moment when space, time, matter, and energy as we know them emerged from an unimaginably hot, dense state nearly 13.8 billion years ago. But there is a question that continues to haunt cosmology. What happened before the Big Bang? It is a question that seems simple, almost childlike, yet it pushes physics to its limits. Because when we ask what came before the beginning of time itself, we are stepping beyond the boundaries of established science. The Big Bang theory is not a theory about an explosion in space. It is a theory about the expansion of space itself. Observations show that galaxies are moving away from each other in all directions. The farther they are, the faster they recede. This expansion implies that in the distant past, everything was closer together. If we rewind the cosmic clock far enough, we reach a time when the universe was incredibly hot and dense. Not a point in space, but a state where space itself was compressed. The earliest moment we can describe with confidence is about 10⁻43 seconds after the beginning. This is known as the Planck time. Before this instant, our current understanding of physics, general relativity, and quantum mechanics breaks down. At the Planck scale, gravity becomes as strong as the other fundamental forces. Space-time itself may have been subject to quantum fluctuations. Our equations cannot handle these conditions. When physicists extrapolate the equations of general relativity backward in time, they arrive at a singularity, a point of infinite density and zero volume. But infinities in physics usually signal that a theory has reached its limits. The singularity is not necessarily a physical object. It is a mathematical artifact of incomplete knowledge. The real mystery lies in what preceded the earliest describable moment. Did time begin at the Big Bang, or did something come before? One of the first breakthroughs in understanding the early universe came in the 1980s with the theory of cosmic inflation. Inflation proposes that a tiny fraction of a second after the Big Bang, around 10⁻36 seconds, the universe underwent a period of extremely rapid expansion. Space itself expanded faster than the speed of light, stretching tiny quantum fluctuations to cosmic scales. This idea explains several puzzles. It accounts for why the universe appears so flat and uniform on large scales. It explains why regions of space far apart have nearly identical temperatures, as observed in the cosmic microwave background radiation. Inflation suggests that the observable universe was once a tiny region that expanded exponentially. But inflation raises its own questions. What triggered inflation? What stopped it? And what existed before it began? Some versions of inflation theory suggest that inflation is eternal. In eternal inflation, quantum fluctuations cause inflation to continue in some regions while stopping in others. Our observable universe would be one bubble among countless others in a vast multiverse. In this scenario, the Big Bang was not the absolute beginning of everything, but the beginning of our local bubble. Other bubbles may have different physical constants, different laws of physics, even different numbers of dimensions. The multiverse is a radical idea, but it emerges naturally from some interpretations of inflation. Yet it is difficult to test. If other universes exist beyond our observable horizon, their signals may never reach us. Another approach comes from quantum cosmology. In 1983, physicists James Hartle and Stephen Hawking proposed the no-boundary hypothesis. According to this idea, the universe has no boundary in time, just as the surface of a sphere has no edge. If you travel south on Earth, you eventually reach the South Pole. But there is no point south of the South Pole. Similarly, time might behave like a spatial dimension near the Big Bang, smoothing out the singularity. In this view, asking what came before the Big Bang is like asking what lies south of the South Pole. The question may be meaningless. Time itself may have emerged with the universe, but this challenges our intuition. We are used to thinking of time as a continuous line stretching infinitely backward and forward. To imagine time having a beginning is deeply unsettling. Other theories propose a cyclic universe. In cyclic models, the universe undergoes endless cycles of expansion and contraction. A previous universe might have collapsed in a big crunch, followed by a bounce that created our own. In these models, the Big Bang was not the absolute beginning, but a transition. One variant is the Fermi-Paradox model, inspired by string theory. It suggests that our universe exists on a three-dimensional brane within a higher dimensional space. Collisions between branes could trigger Big Bang-like events. In this picture, the universe may have existed for eternity in higher dimensions, with periodic collisions generating new expansions. Loop quantum gravity offers yet another perspective. This theory attempts to quantize space-time itself, suggesting that space is composed of discrete units. In loop quantum cosmology, the singularity at the Big Bang is replaced by a quantum bounce. Instead of infinite density, there is a minimum possible volume. The universe may have contracted from a previous phase before rebounding into expansion. If true, our universe might be the aftermath of a previous cosmic epoch. Observational evidence for these ideas remains elusive. The cosmic microwave background provides a snapshot of the universe about 380,000 years after the Big Bang. Tiny temperature fluctuations in this radiation encode information about earlier conditions. Some researchers search for subtle patterns, circular imprints, anomalies, statistical irregularities that might hint at pre-Big Bang physics. So far, no conclusive evidence has emerged. There is also the profound question of causality. If time began at the Big Bang, then causality itself began there. Causes and effects require time to operate. Asking what caused the Big Bang may not make sense if cause and effect relationships did not yet exist. Yet, the human mind resists this conclusion. We are driven to ask why. Why is there something rather than nothing? Why do the laws of physics have the values they do? Some physicists speculate that the universe may have emerged from a quantum fluctuation in a vacuum. In quantum mechanics, empty space is not truly empty. It teems with virtual particles popping in and out of existence. Perhaps the entire universe arose from such a fluctuation, a spontaneous event governed by quantum rules. But what laws governed that vacuum? Where did those laws come from? Every answer seems to push the question one step further back. There is also the puzzle of entropy. The second law of thermodynamics states that entropy disorder tends to increase over time. The early universe appears to have been in a state of extremely low entropy, highly ordered. Why was the initial state so special? If the universe began in a generic high entropy state, it would not have evolved into the structured cosmos we see today. Some argue that inflation explains this by smoothing out irregularities. Others suggest deeper principles yet unknown. The nature of time itself becomes central to the mystery. In everyday experience, time flows from past to future. But in the equations of fundamental physics, time is often symmetric. The arrow of time, the direction in which entropy increases, may be tied to the universe's low entropy beginning. Understanding what happened before the Big Bang may require understanding why time flows at all. The mystery is compounded by the incompatibility between general relativity and quantum mechanics. General relativity describes gravity as the curvature of space-time on large scales. Quantum mechanics describes the behavior of particles and fields on tiny scales. At the Big Bang, both regimes converge. We need a theory of quantum gravity, a unified framework that reconciles these two pillars of physics. Until we have such a theory, our picture of the earliest moments will remain incomplete. Experimental clues may one day come from gravitational waves. Primordial gravitational waves, ripples in space-time generated during inflation, could carry information from fractions of a second after the Big Bang. Detecting their signature in the polarization of the cosmic microwave background would provide powerful evidence for inflation and perhaps insight into pre-Big Bang conditions. So far, such signals remain elusive. The question of what happened before the Big Bang may ultimately force us to rethink our concepts of space and time. Perhaps the Big Bang was not the beginning of existence, but the beginning of our observable patch of reality. Perhaps time itself is emergent, arising from more fundamental timeless laws. Perhaps our universe is one of many, each with its own beginning and end. Or perhaps the notion of before simply does not apply. Among the cosmic mysteries scientists cannot solve, this one strikes at the deepest philosophical roots. It is not just a question about physics, it is a question about existence. When we look up at the night sky, we see light that has traveled billions of years to reach us. We see galaxies as they were long ago. We glimpse the universe's history etched in photons. But the ultimate origin remains hidden behind a veil of mathematical uncertainty. The Big Bang marks the boundary of our knowledge. Beyond it lies speculation, theory, and imagination. Yet, the search continues. Every new observation, every refined measurement, every theoretical breakthrough brings us closer to understanding. The mystery of what happened before the Big Bang is not merely a scientific puzzle. It is a reminder that the universe, vast and ancient as it is, still holds secrets at its very foundation. And perhaps the answer, when it comes, will reshape not only cosmology, but our understanding of reality itself. There is a place in the universe where our laws of physics break down completely. A place where gravity becomes so intense that not even light can escape. A place where time and space trade roles, where the known rules of reality dissolve into mathematical infinities. We can detect these objects. We can measure their mass. We can even photograph their shadows. But what lies inside them remains one of the greatest unsolved mysteries in science. These are black holes. Black holes are not rare cosmic curiosities. They are everywhere. Stellar mass black holes are formed when massive stars collapse at the end of their lives. Supermassive black holes, containing millions or billions of times the sun's mass, sit at the centers of nearly every galaxy, including our own Milky Way. We understand how they form. We understand how they influence their surroundings. We can describe their event horizons with precision. But what happens beyond that horizon, inside the black hole, is a question that strikes at the heart of physics. To understand the mystery, we must begin with gravity. Einstein's general theory of relativity describes gravity not as a force, but as the curvature of space-time caused by mass and energy. Massive objects bend space-time like a heavy ball placed on a stretched rubber sheet. Objects move along the curves created by this bending. A black hole forms when mass is compressed into such a small region that space-time curves inward without limit. At a certain boundary, the event horizon, the escape velocity exceeds the speed of light. Nothing that crosses the event horizon can return. The event horizon is not a physical surface. It is a boundary in space-time, a point of no return. According to general relativity, once matter passes the event horizon, it inevitably collapses toward a singularity at the center, a point of infinite density and zero volume. But infinities are warning signs in physics. They suggest that our equations have broken down. General relativity predicts singularities, but it cannot describe what actually happens at one. At the singularity, gravity becomes infinitely strong. Space-time curvature becomes infinite. The known laws of physics cease to function. This is where the mystery begins. What is a singularity? Is it truly a point of infinite density? Or is it a placeholder for a deeper, unknown physical process? To answer that question, we must confront a fundamental conflict in physics. General relativity governs the large-scale structure of space-time. Quantum mechanics governs the behavior of particles and fields at the smallest scales. Both theories are extraordinarily successful within their domains. but they are incompatible with each other. At the singularity of a black hole, both quantum effects and gravitational effects are equally important. We need a theory of quantum gravity to describe what happens there, and we do not yet have one. The mystery deepens when we consider information. In quantum mechanics, information about a system cannot be destroyed. The evolution of quantum states is unitary, meaning that if you know the complete information about a system at one time, you can, in principle, reconstruct it at any other time. But black holes appear to destroy information. If you throw a book into a black hole, the information contained in its arrangement of atoms seems to vanish beyond the event horizon. If the black hole later evaporates completely, as predicted by Stephen Hawking's theory of black hole radiation, what happens to that information? This is known as the black hole information paradox. In 1974, Stephen Hawking made a groundbreaking discovery. By combining quantum mechanics with general relativity near the event horizon, he found that black holes are not entirely black. They emit a faint radiation, now called Hawking radiation, due to quantum fluctuations at the edge of the horizon. Over extremely long timescales, black holes can lose mass and eventually evaporate completely. But Hawking's original calculations suggested that the radiation emitted is purely thermal random and carrying no information about what fell into the black hole. If that were true, information would be permanently lost when a black hole evaporates. This contradicts quantum mechanics. The paradox has persisted for nearly 5 decades. Many solutions have been proposed. One idea is that information is somehow encoded in subtle correlations within Hawking radiation, too subtle for Hawking's original calculation to capture. Another proposal is the holographic principle. The holographic principle suggests that all the information contained within a volume of space can be described by information on its boundary surface. Applied to black holes, this idea implies that information about infalling matter may be stored on the event horizon itself, encoded in tiny fluctuations of space-time. In this view, the interior of a black hole might be less mysterious than we think. The event horizon becomes a kind of two-dimensional storage device for three-dimensional information. This concept is supported by developments in string theory and the ADS-CFT correspondence, a mathematical framework suggesting that gravity in a higher dimensional space can be equivalent to a quantum field theory on its boundary. If true, it would mean that our understanding of space-time is fundamentally incomplete. Perhaps space-time itself emerges from more basic quantum information processes, but the paradox has not been fully resolved. In recent years, new ideas have emerged, some even more radical. One such idea is the firewall hypothesis. To preserve quantum information, some physicists have proposed that the event horizon may not be smooth, as general relativity predicts. Instead, it might be surrounded by a high-energy firewall that destroys anything attempting to cross it. This would violate the equivalence principle, a cornerstone of general relativity, which states that an observer falling into a black hole should experience nothing unusual at the horizon. If firewalls exist, our understanding of space-time must be revised. Other theories suggest that black holes may not contain singularities at all. Loop quantum gravity proposes that space-time has a discrete structure at the smallest scales. In this framework, the singularity might be replaced by a bounce, a transition to another region of space-time. Some models even suggest that black holes could spawn new universes. In these speculative scenarios, the interior of a black hole might expand into a new cosmos, disconnected from our own. Our universe itself could be the interior of a black hole in a higher dimensional space. There is no direct evidence for this idea, but it illustrates how far-reaching the mystery has become. Observationally, black holes have moved from theoretical curiosities to tangible objects. In 2019, the Event Horizon Telescope released the first image of a black hole's shadow, the supermassive black hole at the center of the galaxy, M87. In 2022, it produced an image of Sagittarius A, the black hole at the center of our own galaxy. These images show a bright ring of glowing plasma surrounding a dark central region, the shadow cast by the event horizon. They confirm general relativity's predictions with remarkable precision, yet they reveal nothing about the interior. Gravitational waves have opened another window. Since 2015, detectors like LIGO and Virgo have observed ripples in space-time produced by merging black holes. These observations confirm that black holes exist and behave as predicted during mergers. But again, they tell us nothing about what lies inside. We can study black holes from the outside, but the interior remains hidden by the event horizon. No signal can escape. Imagine falling into a black hole. From your perspective, crossing the event horizon might feel uneventful if the black hole is large enough. There would be no sudden barrier, no visible surface. But once inside, all paths lead inward. Space and time effectively swap roles. Moving toward the singularity becomes as inevitable as moving forward in time. Within fractions of a second, or perhaps much longer, depending on the black hole's mass, you would reach the center, and then physics would fail. What happens at that moment? Does matter compress into a point? Does it transform into something else? Does it exit into another universe? We do not know. The mystery of black hole interiors is not just about extreme astrophysics. It is about the foundations of reality. Black holes sit at the intersection of gravity, quantum mechanics, thermodynamics, and information theory. They are laboratories for the deepest questions in physics. If we can understand what happens inside a black hole, we may uncover the nature of quantum gravity. We may learn whether information is truly preserved. We may discover whether space-time is fundamental or emergent. The challenge is that direct experiments are impossible. We cannot probe beyond the event horizon. We must rely on theoretical consistency and indirect evidence. In recent years, thought experiments and mathematical models have advanced rapidly. Some physicists believe that the paradox is close to resolution. Others argue that a revolutionary new theory is required. Among all cosmic mysteries scientists cannot solve, the interior of black holes stands as one of the most profound. We can map the cosmos. We can measure the expansion of the universe. We can detect particles born in the first moments after the Big Bang. But the heart of a black hole remains hidden. a region where space and time collapse, where singularities challenge our equations, where information may or may not survive, where the known laws of physics reach their breaking point. Black holes are not just astronomical objects. They are gateways to the unknown. And until we reconcile gravity and quantum mechanics, their deepest secrets will remain beyond the horizon, forever tantalizing, forever unsolved. Across the universe, something is flashing in the dark. Not slowly, not steadily, but in bursts so brief they last only milliseconds. For less than the blink of an eye, these signals erupt with the energy the sun produces over days. Then they vanish, leaving behind only data cryptic spikes recorded by radio telescopes scanning the sky. They arrive from distant galaxies. Some repeat, most do not. Some pulse in strange patterns. Others appear once and are never heard again. These are fast radio bursts, and despite years of study, they remain one of the most puzzling cosmic mysteries scientists cannot fully solve. The story begins quietly in 2007, in a set of archived observations taken by the Parkes Radio Telescope in Australia. Astronomers were combing through old data, searching for pulsars rapidly spinning neutron stars that emit beams of radio waves like cosmic lighthouses. Instead, they found something else, a single, extremely bright pulse lasting just 5 milliseconds. At first glance, it looked like interference, perhaps a stray signal from Earth. But closer analysis revealed a crucial clue. The radio frequencies in the burst arrived at slightly different times, with higher frequencies reaching the telescope before lower ones. This effect is called dispersion. When radio waves travel through space, they pass through clouds of ionized gas plasma. Lower frequency waves are slowed more than higher frequency waves. The more plasma the signal passes through, the greater the delay between frequencies. The dispersion of this mysterious burst was enormous, far greater than could be explained by material within our own galaxy. It had traveled across billions of light years. The burst was named the Lorimer Burst, after astrophysicist Duncan Lorimer, who led the analysis. At first, many astronomers were skeptical. Could it have been a glitch? An unusual form of terrestrial interference? Then more bursts were found. In 2013, additional fast radio burst FRBs were identified in archival data. The phenomenon was real. These bursts were coming from deep space. Each one lasted only a few milliseconds. Each one released an astonishing amount of energy, and each one appeared without warning. The brevity of the bursts immediately constrained their origin. An object cannot vary in brightness faster than light can travel across it. A millisecond corresponds to a region only a few hundred kilometers across. The source had to be compact. This ruled out most large astrophysical objects like stars or galaxies. Neutron stars became the leading candidates. Neutron stars are the remnants of massive stars that have exploded in supernovae. They are incredibly dense, packing more mass than the sun into a sphere about 20 kilometers wide. Some neutron stars are pulsars, emitting regular radio pulses as they spin. Could FRBs be extreme versions of pulsar activity? For years, most FRBs appeared to be one-time events, That suggested catastrophic origins, perhaps the merger of two neutron stars or the collapse of a neutron star into a black hole. But in 2016, everything changed. Astronomers detected an FRB that repeated. FRB 121102 emitted multiple bursts from the same location in the sky. Whatever was producing it had survived. This was a turning point. The repeating FRB was localized to a dwarf galaxy about 3 billion light-years away. Further observations showed that it was associated with a persistent radio source, possibly a nebula powered by a highly magnetized neutron star. Magnetars emerged as prime suspects. Magnetars are neutron stars with magnetic fields trillions of times stronger than Earth's. When their magnetic fields twist and snap, or when their crusts crack in starquakes, they can release enormous bursts of energy. In 2020, a magnetar within our own galaxy, SGR 1935 plus 2154, produced a radio burst remarkably similar to extragalactic FRBs, though less powerful. For the first time, scientists had observed an FRB-like signal from a known magnetar. This strongly suggested that at least some FRBs originate from magnetars. But the story is far from simple. Not all FRBs behave the same way. Some repeat frequently. Others have been observed only once. Some show complex substructure, multiple peaks within a single millisecond burst. Some exhibit periodic activity. FRB 180916, for example, produces bursts in a 16-day cycle, active for about 4 days, then silent for 12. This periodicity hints at a binary system, perhaps a magnetar orbiting a companion star. Other FRBs show extreme polarization, evidence that their radio waves are passing through intense magnetic fields. Some have extraordinarily high rotation measures, indicating that they originate in highly magnetized environments, perhaps near black holes or within dense stellar remnants. The diversity of FRBs suggests that there may be multiple mechanisms at work. Magnetars likely explain many cases, but some FRBs challenge even that model. For example, certain bursts are far more energetic than typical magnetar flares. Others originate in galaxies with little star formation, where young magnetars should be rare. The mystery deepens with each new detection. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, has revolutionized FRB discovery. Its wide field of view allows it to monitor large swaths of sky continuously. Since becoming operational, CHIME has detected hundreds of FRBs. With more data, patterns have begun to emerge. Some FRBs cluster in star-forming regions. Others originate near galactic centers. A few have been traced to globular clusters, dense collections of old stars. Each environment offers clues, but no single explanation fits all observations. The energy scales involved are staggering. In a few milliseconds, an FRB can release as much energy as the sun emits in several days. Yet, because the burst is so brief, the total energy is modest by cosmic standards. The challenge lies in generating that energy so quickly. Theoretical models explore a range of possibilities. Magnetospheric reconnection events in magnetars could release bursts of coherent radio emission, Collisions between neutron stars and exotic compact objects might produce singular bursts. Interactions between neutron stars and surrounding plasma could amplify radio waves through maser-like processes. Some models even consider interactions between black holes and strong magnetic fields. And then there are the more speculative ideas. Could some FRBs be artificial? The possibility is occasionally raised, particularly when unusual periodicity or structure is observed. But there is no credible evidence that FRBs are extraterrestrial signals. Their distribution across the sky and across billions of light years suggests natural origins. Moreover, their energy requirements would far exceed any plausible technological beacon. Still, the fact that the question arises underscores how mysterious they remain. FRBs are not just curiosities. They are powerful tools for cosmology. Because they travel across vast distances, their dispersion measures provide information about the amount of matter they pass through. In fact, FRBs have helped locate much of the universe's missing baryons, ordinary matter that was predicted but not observed directly. By measuring how much each burst is dispersed, astronomers can estimate the density of intergalactic gas. FRBs are becoming probes of cosmic structure, yet the origin of the bursts themselves remains unresolved. Some FRBs show hints of pre-burst activity or follow-up emission. Others exhibit frequency drifts patterns, where the peak frequency slides downward during the burst. These details challenge simple models. The puzzle is compounded by the fleeting nature of FRBs. They last milliseconds. Catching one requires constant vigilance. Pinpointing their exact location requires rapid coordination between telescopes across the world. Each detection is a race against time. Imagine standing on a distant planet in a galaxy billions of light years away. Somewhere nearby, a magnetar's crust fractures. Magnetic fields snap and reconnect. A burst of radio energy explodes outward. For a fraction of a second, that burst outshines entire star systems in radio wavelengths. It travels across intergalactic space for billions of years. Finally, it sweeps past Earth. Our radio telescopes record a brief spike, and then it is gone. The universe is full of these flashes. Hundreds may occur every day across the sky. Most go undetected. We are only beginning to listen carefully enough to notice them. As radio technology improves, more FRBs are being cataloged. New telescopes, like the Square Kilometer Array, promise even greater sensitivity. With larger samples, patterns may clarify. We may discover that FRBs represent several distinct phenomena, or we may find that they are manifestations of a single, versatile process under extreme conditions. For now, they remain enigmatic. They are not predictable. They are not fully understood. They are cosmic whispers from the distant universe. Among the cosmic mysteries scientists cannot solve, fast radio bursts stand out for their brevity and brilliance. They challenge our models of neutron stars and magnetars. They illuminate the distribution of matter between galaxies. They remind us that even in a universe we have studied for centuries, new phenomena can still appear unexpectedly. A flash, a millisecond, a signal from billions of light years away, then silence, and a question mark where certainty should be. Look around you. Everything you see, every atom in your body, every star in the sky, every galaxy scattered across the universe is made of matter. Solid, tangible, familiar matter. Protons, neutrons, electrons, atoms built into molecules, molecules assembled into worlds. But according to the laws of physics, none of this should exist, because in the beginning, the universe should have created equal amounts of matter and antimatter, and if that were true, they should have annihilated each other completely, leaving behind nothing but radiation, no stars, no galaxies, no planets, no life. Yet, here we are. This is the mystery of the missing antimatter, one of the deepest unsolved problems in modern physics. To understand the paradox, we must go back to the earliest moments after the Big Bang. In the first fractions of a second, the universe was unimaginably hot and dense. Energy dominated. Particles and antiparticles were being created constantly from pure energy, in accordance with Einstein's famous equation E = mc². For every particle created, an antiparticle should have been created as well. Antimatter is not science fiction. It is real, well understood, and routinely produced in laboratories. For every type of particle, there exists an antiparticle with the same mass but opposite charge. The electron has the positron. The proton has the antiproton. The neutron has the antineutron. When a particle meets its antiparticle, they annihilate, converting their mass back into energy in the form of photons. The laws of physics, as we understand them, are almost perfectly symmetric between matter and antimatter. In the early universe, matter and antimatter should have been created in equal amounts. As the universe expanded and cooled, particles and antiparticles would have met and annihilated. Almost all of them should have vanished. The only thing left would be radiation. Yet, something extraordinary happened. For every billion pairs of matter and antimatter particles that annihilated each other, there was one extra matter particle left over. 1 in a billion. That tiny imbalance, one extra proton for every billion proton-antiproton pairs, was enough. As the universe expanded further, those leftover matter particles became the building blocks of everything we see today. But why was there an imbalance at all? Why wasn't the universe perfectly symmetric? This is the matter-antimatter asymmetry problem. The laws of physics do allow for slight asymmetries. In the 1960s, physicists discovered that certain subatomic processes violate a symmetry known as CP symmetry, charge conjugation, and parity. Charge conjugation refers to swapping particles with antiparticles. Parity refers to flipping spatial coordinates. If CP symmetry were perfect, the laws of physics would treat matter and antimatter exactly the same. But experiments showed that certain decays of particles, called kaons, behave slightly differently for matter and antimatter. This was a breakthrough. It meant that the universe does contain small asymmetries in its fundamental laws. Later, similar CP violation was observed in particles known as B mesons. These findings suggested that the laws of physics could, in principle, produce an imbalance between matter and antimatter. However, there is a problem. The amount of CP violation observed in laboratory experiments is far too small to account for the vast matter dominance of the universe. The standard model of particle physics predicts some asymmetry, but not nearly enough. There must be additional sources of asymmetry that we have not yet discovered. Physicists have proposed many possibilities. One leading idea involves processes in the early universe, known as baryogenesis, the generation of baryons, the class of particles that includes protons and neutrons. For baryogenesis to occur, three conditions, known as the Sakharov conditions, must be satisfied. First, there must be processes that violate baryon number, meaning they allow the creation or destruction of baryons. Second, CP symmetry must be violated. Third, these processes must occur out of thermal equilibrium. The standard model satisfies these conditions to some extent, but not enough. This is the Hubble tension. To understand why this matters, we must first understand what the Hubble constant represents. The Hubble constant describes the current rate of expansion of the universe. It tells us how fast galaxies are moving away from each other per unit of distance. If a galaxy is twice as far away, it should be receding roughly twice as fast. The constant is usually expressed in kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. If the Hubble constant were 70 kilometers per second per megaparsec, it would mean that for every megaparsec of distance, a galaxy's recessional velocity increases by 70 kilometers per second. Measuring this number precisely is crucial. It affects our estimates of the universe's age, its size, and its future fate. For decades, astronomers refined the value, narrowing it down with better instruments and better data. Then came the revolution in precision cosmology. There are two primary ways to measure the Hubble constant. The first is called the local method. This approach measures distances to relatively nearby galaxies using standard candles objects of known intrinsic brightness. One of the most important standard candles is the Cepheid variable star. Cepheids are stars whose brightness varies periodically. The period of their variation is directly related to their intrinsic luminosity. By measuring the period, astronomers can determine how bright the star truly is. Comparing that to how bright it appears allows them to calculate its distance. Cepheids can be used to calibrate distances to nearby galaxies. From there, astronomers use type Ia supernovae, another type of standard candle, to extend distance measurements much farther into space. By measuring the distances and recessional velocities of many galaxies, scientists can calculate the Hubble constant. The most precise local measurements, led by astronomer Adam Riess and his team, yield a Hubble constant of about 73 kilometers per second per megaparsec. The second method is entirely different. Instead of measuring nearby galaxies, it looks at the early universe. The cosmic microwave background, the afterglow of the Big Bang, provides a snapshot of the universe when it was only about 380,000 years old. Satellites like WMAP and Planck have mapped this radiation in exquisite detail, measuring tiny temperature fluctuations across the sky. These fluctuations encode information about the universe's composition and geometry. By fitting these observations to the standard cosmological model, the lambda, cold dark matter model, scientists can extrapolate forward in time and predict what the Hubble constant should be today. This method yields a value of about 67 kilometers per second per megaparsec. At first glance, the difference between 73 and 67 may not seem dramatic, but in precision cosmology, it is enormous. The discrepancy is far beyond the margin of error of either method. Both measurements are highly refined. Both are internally consistent, yet they disagree. The universe appears to be expanding faster when measured locally than when inferred from the early universe. This is the Hubble tension. At first, scientists suspected systematic errors. Perhaps Cepheid distances were slightly off. Perhaps supernova calibrations needed adjustment. Perhaps there were subtle biases in the cosmic microwave background analysis. But as measurements improved, the tension persisted and even grew stronger. Independent teams using different techniques confirmed both results. Gravitational lensing, time delays, another method involving light bending around massive galaxies, yield values closer to the local measurement. Meanwhile, baryon acoustic oscillations and large-scale structure surveys tend to agree with the early universe prediction. The problem refuses to disappear. If both methods are correct, then something is wrong with our cosmological model. The standard model of cosmology assumes that the universe is composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy, with dark energy behaving as a cosmological constant. This model has been extraordinarily successful. It explains the cosmic microwave background, galaxy clustering, and the large-scale structure of the universe. But the Hubble tension suggests that it may be incomplete. One possibility is that dark energy is not constant. If dark energy evolved over time, changing its strength or behavior, it could alter the expansion history in subtle ways. Another idea involves additional forms of radiation in the early universe. Perhaps there were extra relativistic particles, sometimes called dark radiation, that influenced the expansion rate shortly after the Big Bang. These hypothetical particles would have left subtle imprints in the cosmic microwave background. So far, no definitive evidence for such particles has emerged. Some researchers propose that neutrinos, those ghostly particles that barely interact with matter, may hold clues. If neutrinos have properties different from what we currently believe, they could affect the early expansion rate. Others suggest that modifications to gravity itself may be required. Perhaps general relativity needs adjustment on cosmic scales. More exotic ideas include interactions between dark matter and dark energy, or phase transitions in the early universe that temporarily altered expansion. Each proposal attempts to reconcile the discrepancy without destroying the overall success of cosmology, but none has yet provided a definitive solution. The stakes are high. If the Hubble tension is real, it could point to new physics beyond the standard model of cosmology. It could signal a deeper layer of reality waiting to be uncovered. Or it could reveal hidden complexities in dark energy. The age of the universe is also at stake. If the Hubble constant is higher, the universe is slightly younger. If lower, slightly older. The difference may be on the order of hundreds of millions of years, small compared to 13.8 billion years, but significant for precision cosmology. The tension is not just a technical issue. It is a potential sign that our understanding of the universe's history is incomplete. Imagine two clocks measuring the age of the universe. One looks at ancient light from the dawn of time. The other measures the motion of nearby galaxies. Both are exquisitely precise. Both are reliable. Yet, they disagree. It is as if the universe is telling us that something important is missing. Some physicists believe the solution may lie in early dark energy, a brief episode in the early universe when dark energy temporarily contributed more to the total energy density. This could alter the expansion rate inferred from the cosmic microwave background, bringing it closer to local measurements. Others argue that the discrepancy may eventually shrink as measurements become even more precise. New telescopes are poised to provide better data. The James Webb Space Telescope is improving distance measurements using Cepheids and other standard candles. The Vera C. Rubin Observatory will map billions of galaxies, refining large-scale structure measurements. Future cosmic microwave background experiments will measure fluctuations with unprecedented precision. The hope is that new data will either resolve the tension or sharpen it further. If the discrepancy grows stronger, the case for new physics becomes harder to ignore. The Hubble tension is a reminder that even in an era of precision cosmology, fundamental mysteries remain. We have mapped the cosmic microwave background. We have detected gravitational waves. We have imaged black holes. Yet, something as basic as the current expansion rate of the universe remains uncertain. Among the cosmic mysteries scientists cannot solve, this one is particularly unsettling because it challenges a model that has worked so well. It is not a distant anomaly in a remote galaxy. It is a disagreement at the heart of cosmology itself. Perhaps the tension will fade as data improves, or perhaps it will lead to a paradigm shift. In the past, discrepancies in measurements have led to revolutions in physics. The precession of Mercury's orbit helped confirm general relativity. The ultraviolet catastrophe led to quantum mechanics. The accelerating expansion of the universe revealed dark energy. The Hubble tension may be the next crack in the foundation. Or it may be a subtle misunderstanding waiting to be clarified. For now, the universe appears to be expanding at two different speeds, depending on how we measure it. And until we reconcile those measurements, the true rate of cosmic expansion remains one of the most pressing unsolved mysteries in modern science. The universe is stretching, galaxies are drifting apart, and somewhere in the data, hidden in the difference between 67 and 73, lies a clue to physics beyond our current understanding. A small discrepancy, a big question, and a mystery that refuses to be ignored. Time feels obvious. It flows. It moves forward. It carries us from past to present to future. Clocks tick, hearts beat, stars are born and eventually die. Every experience we have is embedded in the passage of time. And yet, when physicists attempt to describe time at the deepest level, it begins to dissolve. Is time fundamental, woven into the fabric of the universe like space? Or is it an illusion, an emergent property arising from something more basic? Why does time have a direction? Why can we remember the past but not the future? And why do the fundamental equations of physics seem almost indifferent to its flow? The nature of time is one of the most profound mysteries scientists cannot solve. In everyday life, time appears simple. It flows uniformly, ticking second by second. But physics has shown that time is far stranger than intuition suggests. In the 17th century, Isaac Newton treated time as absolute. It flowed at the same rate everywhere, independent of motion or gravity. The universe was a stage, and time was a universal clock, ticking identically for all observers. Then came Einstein. In 1905, Einstein's theory of special relativity shattered the idea of absolute time. Time, he showed, is not universal. It depends on motion. If you travel close to the speed of light, time slows down relative to someone at rest. This is not science fiction. It is measurable. Astronauts on the International Space Station age slightly more slowly than people on Earth. Particles accelerated in laboratories live longer than they would at rest. Time is relative. In 1915, Einstein's general theory of relativity revealed something even more astonishing. Gravity affects time. The stronger the gravitational field, the slower time passes. Clocks at sea level tick slightly more slowly than clocks on mountaintops. GPS satellites must account for relativistic time dilation to function accurately. Time is not separate from space. It is part of space-time, a four-dimensional fabric that bends and curves in the presence of mass and energy. But relativity does not tell us why time flows in one direction. The equations of classical mechanics, electromagnetism, and even quantum mechanics are mostly time-symmetric. If you reverse the direction of time in these equations, they still work. At the fundamental level, physics does not seem to distinguish past from future, yet our experience does. We remember the past, but not the future. Eggs break, but do not spontaneously reassemble. Smoke spreads out, but does not gather itself back into a cigarette. This asymmetry is known as the arrow of time. The arrow of time is closely tied to the second law of thermodynamics. The second law states that entropy, a measure of disorder, tends to increase over time in a closed system. A broken glass is more disordered than an intact one. A mixed gas is more disordered than separated gases. Entropy increases because there are vastly more ways for a system to be disordered than ordered. But this raises a profound question. If the laws of physics are time-symmetric, why was the universe in such a low entropy state at the beginning? The early universe, as revealed by the cosmic microwave background, was remarkably uniform and ordered. That low entropy beginning set the stage for entropy to increase over time. But why was it so special? Why didn't the universe begin in a high entropy, chaotic state? Some cosmologists argue that inflation explains this by smoothing out irregularities. Others believe the low entropy beginning is a deeper mystery, perhaps tied to unknown principles of quantum gravity. The arrow of time may ultimately depend on the initial conditions of the universe, and that leads back to the question of what happened before the Big Bang. Time is even more puzzling in quantum mechanics. In quantum theory, the evolution of a system is described by the Schrödinger equation, which is time symmetric. If you reverse time, the equation still holds. Yet when we measure a quantum system, the wave function appears to collapse, choosing a specific outcome from many possibilities. This collapse introduces irreversibility. Before measurement, the system exists in a superposition of states. After measurement, it is in a definite state. Why does this happen? Some interpretations of quantum mechanics, such as the many worlds interpretation, avoid collapse altogether. Instead, they suggest that all possible outcomes occur in branching universes. In this view, time may be a branching tree, with countless futures unfolding simultaneously. Other interpretations suggest that time itself may be emergent from quantum entanglement. In recent years, physicists have proposed that space-time may arise from patterns of quantum information. If space-time is emergent, perhaps time is not fundamental. Perhaps it is a macroscopic phenomenon arising from deeper timeless laws. In certain formulations of quantum gravity, such as the Wheeler-DeWitt equation, time does not appear at all. The equation describing the quantum state of the universe has no time parameter. This has led some physicists to propose that, at the deepest level, the universe is timeless. Time, in this view, emerges only when we consider subsystems interacting with each other. It is a relational property, not a fundamental dimension. This idea is deeply counterintuitive. We experience time intimately. We age. We remember. We anticipate. To suggest that time is not fundamental feels almost absurd. Yet, physics has repeatedly shown that intuition can be misleading. Consider black holes. Inside a black hole, the roles of space and time appear to swap. Once past the event horizon, moving toward the singularity is as inevitable as moving forward in time. The singularity itself lies in the future of anything that crosses the horizon. In extreme gravitational fields, time behaves in ways that defy everyday understanding. Then there is the question of time travel. General relativity allows for solutions with closed, time-like curves, paths through space-time that loop back on themselves. In theory, such curves could allow travel into the past. Wormholes, hypothetical tunnels through space-time might connect distant regions or different times. But these solutions require exotic matter with negative energy, density which has not been observed in macroscopic quantities. Moreover, time travel to the past introduces paradoxes. The grandfather paradox asks, what happens if you travel back in time and prevent your own existence? Some physicists propose that the universe enforces consistency only. Self-consistent events can occur. Others argue that quantum mechanics may allow branching timelines, avoiding paradoxes. But as of now, time travel remains speculative. Another mystery concerns the beginning of time. If time began at the Big Bang, asking what came before may be meaningless. But some models suggest that time extends beyond the Big Bang, perhaps in a cyclic or bouncing universe. If time is infinite, why does it feel linear? Why does it have a direction? Some researchers propose that the arrow of time may be local rather than global. In a sufficiently large multiverse, regions of increasing entropy could exist alongside regions of decreasing entropy. Observers would naturally find themselves in regions where entropy increases. Others suggest that time's arrow is linked to quantum decoherence, the process by which quantum systems lose coherence as they interact with their environment. As systems become entangled with their surroundings, superpositions appear to collapse, creating an effective arrow of time. But these ideas remain debated. The mystery of time touches every branch of physics. Relativity tells us time is relative and malleable. Thermodynamics tells us time has a direction. Quantum mechanics suggests time may not even be fundamental. Cosmology ties time's origin to the birth of the universe. And yet, we still do not fully understand what time is. Is it a dimension like space? Part of a four-dimensional block universe where past, present, and future coexist? In the block universe view, time does not flow. All moments exist equally. Our perception of flow is an illusion. Or is time genuinely dynamic, with the future not yet determined? Some physicists advocate for a growing block universe where the past and present exist, but the future does not. Others propose that time emerges from entanglement and information processing. Imagine stepping outside the universe and viewing space-time as a whole. Would you see a static, four-dimensional structure like a frozen sculpture? Or would you see something evolving? Our brains are wired to perceive change. We experience time through memory and anticipation. But memory itself depends on entropy and physical processes. If entropy did not increase, we might not perceive time at all. Perhaps time is inseparable from change. Perhaps without change, time has no meaning. Among the cosmic mysteries scientists cannot solve, the nature of time stands as one of the most fundamental. It is not a distant phenomenon in a remote galaxy. It is the backdrop of every experience. And yet, at the deepest level, it may not exist in the way we imagine. The equations of quantum gravity may one day reveal whether time is emergent or fundamental. Experiments probing entanglement and space-time geometry may provide clues. Cosmological observations may shed light on time's origin. Until then, we remain suspended in a flow we do not fully understand. Seconds tick by, stars evolve, galaxies drift apart, entropy increases, and time, mysterious and relentless, carries us forward, whether it is fundamental or an illusion, a dimension, a process, or a byproduct of deeper laws. The clock keeps ticking, but what it truly measures remains one of the deepest unsolved mysteries in the universe. The universe is vast beyond comprehension. Our Milky Way galaxy alone contains hundreds of billions of stars. Many of those stars host planets. In the last 3 decades, astronomers have confirmed the existence of more than 5,000 exoplanets, and statistical analysis suggests there may be trillions of planets in our galaxy alone. Many of them orbit in the so-called habitable zone, where liquid water could exist. Some are rocky worlds similar in size to Earth. Others orbit long-lived stars that shine steadily for billions of years. Given these numbers, life should not be rare. And if life is common, then intelligent life should have arisen many times across cosmic history. If that is true, then where is everyone? This is the Fermi Paradox, one of the most haunting cosmic mysteries scientists cannot solve. The paradox is named after physicist Enrico Fermi, who in 1950 reportedly asked a simple question during a lunchtime conversation: where is everybody? Fermi's reasoning was straightforward. The Milky Way is about 13 billion years old. Even if intelligent civilizations arose only rarely, there has been plenty of time for them to spread across the galaxy. A civilization capable of interstellar travel, even at modest speeds, could colonize the entire Milky Way in tens of millions of years. A blink of an eye on cosmic timescales. Yet, we see no evidence of such civilizations, no alien megastructures, no star-spanning empires, no unambiguous signals from deep space. The silence is deafening. To quantify the puzzle, astronomer Frank Drake formulated an equation in 1961. The Drake equation estimates the number of communicative civilizations in the galaxy based on factors such as star formation rate, the fraction of stars with planets, the number of habitable planets per system, the fraction where life arises, the fraction where intelligence evolves, the fraction that developed detectable technology, and the average lifetime of such civilizations. Many of these factors remain uncertain. But with current knowledge of exoplanets, the first few terms, stars and planets, are no longer speculative. We now know that planets are common. Small, rocky planets are common. Habitable zones are common. This strengthens the paradox. If life arises easily under suitable conditions, then microbial life may be widespread. If evolution tends to produce complexity, then intelligence may not be extraordinarily rare. And if intelligent civilizations develop technology, some may eventually attempt communication. So why haven't we detected anything? One possibility is that life itself is extraordinarily rare. Perhaps the origin of life abiogenesis is an almost impossible event. Earth may have been incredibly lucky. Even though planets are common, the exact combination of chemistry, energy sources, environmental stability, and time required to spark life may be vanishingly improbable. If so, we may be alone simply because life rarely begins. Another possibility is that simple life is common, but complex life is rare. On Earth, life appeared relatively quickly after the planet cooled, but for billions of years it remained microbial. Multicellular organisms appeared only about 600 million years ago. Intelligent life capable of technology emerged only in the last few 100,000 years. Evolution does not necessarily favor intelligence. It favors survival and reproduction. Perhaps complex, intelligent organisms are evolutionary accidents. But even if intelligence is rare, given the vast number of stars in the galaxy, one might still expect at least a few advanced civilizations, unless something prevents them from surviving long enough to spread. This leads to one of the most unsettling ideas: the Great Filter. The Great Filter is a hypothetical barrier in the evolutionary path from simple matter to advanced, spacefaring civilization. It could lie behind us or ahead of us. If it lies behind us, then one of the steps, perhaps the origin of life or the emergence of intelligence, is extremely unlikely. We are rare survivors. If it lies ahead, then advanced civilizations inevitably self-destruct before spreading across the galaxy. Nuclear war, environmental collapse, artificial intelligence gone wrong, unforeseen technological catastrophes. The Great Filter hypothesis is deeply sobering. It suggests that the silence of the cosmos may be a warning. Another possibility is that advanced civilizations are out there, but they choose not to communicate. Perhaps they follow a kind of cosmic non-interference principle, avoiding contact with less advanced species. This idea, sometimes called the zoo hypothesis, suggests that Earth is being observed but not contacted. There is no evidence for this idea, but it remains a speculative possibility. Others suggest that advanced civilizations may communicate in ways we do not recognize. We have searched primarily for radio signals, but technology evolves quickly. Humanity's own radio emissions are becoming less detectable as we shift to fiber optics and targeted transmissions. An advanced civilization might use communication methods beyond our understanding: neutrinos, gravitational waves, or entirely new physics. There is also the possibility that civilizations do not expand aggressively. Perhaps most intelligent species focus inward on virtual realities or sustainable local environments. Interstellar travel is extraordinarily challenging. Even at a fraction of the speed of light, journeys between stars would take decades or centuries. The energy requirements are immense. The dangers are numerous. Maybe the galaxy is not teeming with colonizers, because colonization is not an inevitable goal. But even without colonization, one might expect some detectable signs. Large-scale engineering projects, such as Dyson spheres or star lifting, could produce observable anomalies. Searches for unusual infrared signatures around stars have found no convincing evidence of galaxy-spanning megastructures. Perhaps the simplest explanation is that intelligent civilizations are rare in space and time. Civilizations may arise and fall within relatively short windows. The galaxy is vast, and the timescales are immense. Two civilizations separated by thousands of light years and millions of years in time may never overlap. The Milky Way is 100,000 light years across. Signals travel at the speed of light. If a civilization broadcasts for a few thousand years before going silent, the chances of us being within range at the right time are slim. There is also the possibility that we have not searched long enough. Modern radio SETI efforts have only been underway for about 60 years, a blink of an eye. We have surveyed only a small fraction of the sky at limited frequencies. Our listening is sporadic and incomplete. The cosmic ocean is vast. We have dipped only a small cup into it. The discovery of exoplanets has intensified the paradox. Planets like Proxima Centauri b orbit the nearest star to the Sun. Others, such as the TRAPPIST-1 system, contain multiple Earth-sized worlds in the habitable zone. Future telescopes may analyze the atmospheres of these planets for biosignatures, oxygen, methane, or other chemical imbalances indicating life. If we detect life elsewhere, even microbial life, the paradox will sharpen. If simple life is common, but intelligent life is absent, that would suggest the great filter lies between microbes and intelligence. If we find no life at all, it may suggest that abiogenesis itself is rare. The Fermi Paradox also intersects with deeper philosophical questions. Are we early? The universe is 13.8 billion years old, but it may remain habitable for trillions of years. Red dwarf stars burn for trillions of years, far longer than our sun's lifespan. Perhaps intelligent life will be far more common in the distant future. Perhaps we are among the first. If so, the silence is not surprising. We may be pioneers in a still young cosmos. The paradox remains unresolved because every possible explanation involves unknowns. We do not know how common life is. We do not know how common intelligence is. We do not know how long civilizations last. We do not know what technologies advanced beings might use. We do not know whether they would choose to communicate. And yet, the silence persists. We have scanned the skies for radio signals. We have searched for optical laser pulses. We have looked for anomalies in stellar light curves. So far, nothing definitive. Among the cosmic mysteries scientists cannot solve, the question of whether we are alone may be the most personal. It is not just about physics. It is about our place in the universe. If we are alone, then life on Earth carries extraordinary significance. If we are not, then somewhere out there, other minds are asking the same questions. The paradox forces us to confront both possibilities. Imagine a galaxy filled with silent worlds, planets orbiting distant stars, their surfaces bathed in alien sunlight. Some may host oceans, some may harbor forests, some may teem with microbial life. Yet across the vast distances between stars, no voices carry. Or perhaps, somewhere in the dark, signals are traveling toward us right now, radio waves or laser pulses crossing light years. We simply have not detected them yet. The Fermi Paradox remains unresolved because the universe is vast and our knowledge is incomplete. It may be that the answer is simple and mundane, or it may be that the silence conceals something profound. Until we find evidence, either of life elsewhere or of its absence, the question endures. Where is everybody? In the silence between the stars, the mystery lingers. A paradox born of abundance. A universe filled with planets. A cosmos old enough for civilizations to rise and fall countless times. And yet, For now, only one known world with minds capable of wondering. The search continues. Radio telescopes listen. Space telescopes analyze distant atmospheres. Probes explore our own solar system for microbial life. The question is not merely scientific, it is existential. Are we alone in the universe? Or are we simply not listening well enough? Until we know, the Fermi Paradox stands as one of the deepest and most haunting cosmic mysteries scientists cannot solve.